Hello everyone, myself Rajeshwari Oza. Today I am here to explain about the third dimension in carbon. As I say, this third dimension in carbon, that is related to stereochemistry, which I want to explain some of the points related to stereochemistry here today. So we can see here I am explaining about the stereoisomers and the type of stereoisomers. You can see when we are saying about the same molecular formula but different structure is there, that is the stereochemistry which we are describing here. These are the isomers which have the different type of compounds but with the same molecular formula. Here again two types are there. One is a constitutional isomers and another is a stereoisomers. In constitutional isomers, we can see only the difference between these two is about the connectivity, that how they are connecting with each other. So here you can see these are the isomers whose atoms have a different type of a connectivity. We can say a different type of a connectivity means their connectivity with the carbon atom that is different. Here in this one of the example of C4H10O, we can see these two examples are here. One of the hydroxy group, OH group, and another is related with the ether compound. So first one is a 1-butanol and second is a diethyl ether. In this 1-butanol, we can see this is a functional group, hydroxy group is present. In this diethyl ether, this is a ether group which is present. So we can say these are the isomers whose atoms have a different type of a connectivity. Here the connectivity with the carbon of the functional group with the functional group that is different. So these type of isomers which are known as a constitutional isomers. Now mainly we are here to discuss about the stereoisomers. These stereoisomers are isomers that have the same type of a connectivity but that differ in the arrangement of their atoms in space. In space atoms का जो arrangement है वो connectivity जो है that is say differ in the arrangement only but connectivity is the same. Again here these isomers or these stereoisomers are of two types. First one is a enantiomer and second is a distereomers. Just remember enantiomer and distereomer, what are the differences between that? Whenever we are saying about the enantiomers, that are the non-superimposable mirror images of each other, we can easily explain this thing that whenever the compound we are seeing it is in a mirror, at that time these are the mirror images of each other. We can see like that also, these are the mirror images of each other but these are non-superimposable of each other. So these are known as a enantiomers. What I am saying to you, that what is the enantiomers? That stereoisomer which are non-superimposable mirror images of each other. Simultaneously the second type we are saying about the distereomers. These are the stereoisomers that are not mirror images of each other. So what is the main basic difference between the enantiomers and distereomers is that enantiomers are non-superimposable mirror images of each other and distereomers are not mirror images of each other. So these are the types of stereoisomers which is a enantiomers and distereomers. Now what we can see, this is a simple assembly of a polarimeter. We know that whenever is there any type of a light source is there, when this light source it has an ordinary type of a light which vibrates in all direction. But when we pass it from the polarizer it changes into plane polarized light, in which you can see this plane polarized light it vibrates only in the one plane. Ordinary light vibrates in all the plane, but when we pass it from the polarizer it is changing into a plane polarized light which is also known as a PPL. Now we have taken the tube which is with the solution of one type of a enantiomer. This may be a R enantiomer, this may be a S enantiomer. When we are passing this plane polarized light from this tube which is filled with the solution of one enantiomer, it rotates in the one of the direction. Means this direction may be a clockwise direction or it may be an anti-clockwise direction. And this is an analyzer where we can see. So this is the assembly of a polarimeter in which after passing the ordinary light from the polarizer, we can change it into a plane polarized light which will be shown afterwards about the clockwise or anti-clockwise direction. Now this is the next point which is discussing about the when we have to describe or determine about the enantiomeric axis. So the enantiomeric composition of a sample, it may be described by the enantiomeric axis which is denoted by the EE and which describe the axis of one enantiomer over the other. So enantiomeric axis we can calculate it with the help of the S minus R upon S plus R into 100%, and where R and S, these are the compositions of the R and S enantiomers. Correspondingly, if we have to calculate about the distereomeric axis, at that time we have to see about the distereomer composition of a sample, which can again be determined by the distereomeric axis, which is denoted by DE, and it refers the axis of one distereomer over the other, which can be calculated with the help of this formula DE SS minus SR upon SS plus SR into 100%, and these S star S and S star R, these are the compositions of the distereomers respectively. So in this way, by these formula we can calculate about the enantiomeric axis and distereomeric axis. In enantiomeric axis, where we are saying about the axis of one enantiomer over the other. In the distereomeric axis, we are saying about the axis of one distereomer over the other. Now this is the specific rotation, which is denoted by alpha d20 is equal to alpha upon LC. This alpha d20, it is the specific rotation of sodium D line at 20 degree, alpha which is a observed rotation at 20 degree, and L is a cell length in decimeter, and 1 decimeter is equal to 10 centimeters. C is a concentration of sample solution, which is in gram per ml. Here we can see one of the example of glyceraldehyde. If we are saying about the racemic mixture, then racemic mixture is a combination of the plus form and minus form. Here you can see, if we are taking about the 50% of plus glyceraldehyde and 50% of minus glyceraldehyde, means both of the total it's combined like a plus minus glyceraldehyde. Specific rotation for this plus glyceraldehyde, its value of specific rotation is plus 8.7 degree. At the same time, when we are saying about the minus glyceraldehyde, then specific rotation value is minus 8.7. That's why total specific rotation of glyceraldehyde form, which have the plus minus glyceraldehyde, that value will be 0, that is in the racemic mixture. So we can understand about the racemic mixture, there are both forms are there in the form of a 50-50%. So by the specific rotation we can calculate about that ki specific rotation of the racemic mixture will be 0, because it's have the first one plus 8.7, value of the minus glyceraldehyde, it's a minus 8.7. So total racemic mixture value of the specific rotation will be 0. Now here you can see the simplest example of enantiomerism, where we are saying about the chirality. As everybody knows about this chirality, and we are saying about the chiral carbon, the carbon which have 4 different type of groups attached to the carbon with this 4 valency. At that time this is known as a chiral carbon or asymmetric carbon atom, and it represents by the chirality also. So in this example you can see we have taken 2 compounds or 2 molecules. First one is a cis 1,2-dimethyl cyclopentane, and another one is a trans 1,2-dimethyl cyclopentane. This cis 1,2-dimethyl, why it's a cis and why that is a trans, you can see easily that these 2 groups, CH3 and CH3 group, these are on the same side, and hydrogen on the same side, that's why it's a cis. When we are saying hydrogen and CH3 group are present on opposite side, at that time it is a trans 1,2-dimethyl cyclopentane. In this cis 1,2-dimethyl cyclopentane, it's a achiral type of a compound, and that's a chiral type of a compound. Why it is achiral? You can see easily that here is a plane of symmetry is present in this compound, which is showing about that it's a achiral type of a compound. When we are saying about the stereoisomers of 1,2-dimethyl cyclopentane, in the cis isomer there is no enantiomers, it is achiral. The object and mirror image, these are superimposable. You can see because these 4 groups are the same. Whenever you put this image on this one, that it will be the superimposable. These are non-superimposable nahi hai. To iska matlab ye enantiomers nahi hai. In this example we can see easily that this cis 1,2-dimethyl cyclopentane, it can't be enantiomers, it can't show the enantiomers because these are superimposable on each other. But at the same time, if we are taking and we are saying about the trans 1,2-dimethyl cyclopentane, in this example which you can see, these CH3 groups are present on opposite sides. It's a chiral type of a compound. This trans isomer is a chiral compound, and it can exist in either of two non-superimposable enantiomeric forms, means one form can't be superimposed on another. That's why these are the non-superimposable mirror images of each other. That's why these are the enantiomers, and this trans isomer is a chiral, and it can exist in these type of two type of non-superimposable enantiomeric forms. Now the next thing, one of the most important thing with the related with the one of the example of 2-butanol, and we are saying about the Fischer projections of 2-butanol. In this example, you can see easily in the first example we are saying about the S2-butanol. S2-butanol, and we have done the rotation, these rotation by the 90-degree rotation, 180-degree rotation, and again the 180-degree rotation in the plane of the paper. In this, when we are doing the rotation by 180 degree out of the plane of the paper and in the plane of the paper, but when we are doing the out of the plane of paper and it gives the enantiomer, this type of a process is not allowed. But when we are doing the rotation by 180 degree in the plane of the paper, at that time it's a allowed process. So firstly we are again coming on the S2-butanol, and just remember one thing, whenever we are giving the numbering to these compounds to determine about that this is a R or S configuration, at that time in Fischer projection, if the groups are present on vertical line, then it is okay, it is about the fourth priority group. If the fourth priority group is present on the vertical line, then whatever configuration you are getting, that's the correct configuration. But if the fourth priority group is present on the horizontal line, at that time what happens? If the fourth priority group is present on horizontal line, then you just reverse that order. In that we can see that provided this is the lowest priority group, it is on the vertical line, so clockwise path, if it is a 1, 2, 3 like, means it's a clockwise direction, it's showing R configuration. Or if the fourth priority group, it is present in the horizontal line, then what you have to do, you have to just reverse these assignment, whatever you are getting, you have to reverse this assignment, means R will be changed into a S configuration and S configuration will be changed into a R configuration in that way. So here you can see this is the rotation done by the 90 degree in the plane of the paper, it gives the enantiomer, but this is not allowed type of a process. As 2-butanol, you can see here a 90 degree rotation has been done. In the second example, again you can see this S2-butanol which is changing into a R2-butanol. This is a 180 degree rotation out of the plane of the paper is done, which is also not allowed process. But in the last example, you can see that this R2-butanol, which has the rotation by 180 degree in the plane of the paper, and it's a allowed process. It retains the original configuration as it is, because here it was a R2-butanol and again you are getting the R2-butanol. It means original configuration is there and the rotation is 180 degree. Hydroxy group will go on that side, hydrogen will come on that side, and CH3 and CH2 also in the 180 degree rotation. So these are the Fischer projections of 2-butanol, that whenever you have to get the same type of a configuration, at that time what you have to do. In the Fischer projection 90 degree rotation it is not allowed, here the 180 degree rotation is allowed, but in that 180 degree rotation also you have to see that 180 degree rotation should be in the plane of the paper, which is a allowed process. And if you are doing is out of the plane of the paper and it gives the enantiomer, then it's a not allowed type of a process. So this is the Fischer projection of one of the example of 2-butanol. Now see, we are saying about the optical isomers which may have the differ in the physiological activity. I have taken one of the simplest example of optical isomers of amino acid asparagine. This asparagine, you can see here it has the S configuration in this structure, in the next structure it has the R configuration. So only because of the configuration which is changed, these have the total different type of a property. It is bitter in taste and it is sweet in taste. And the presence of both the enantiomers of the thalidomide in a drug formulation led to birth defects in the children of some women who took the substance during the pregnancy. Here in below you can see this is a S thalidomide structure, and here it's a R thalidomide structure, and in between it says a chiral enol form is there. And even if the pure R form was given to patients, because firstly when we are giving the R and S form both, at that time it affects, and that type of a defects we can see in the pregnancy pregnancy, but if only the pure R form is given, at that time also what happens, this creates the mutagenic S isomer was formed by the racemization. Again I am saying about the before that I described about the racemic mixture. So here if we are using only the R form, which is the pure form, but again this is forming by the racemization S isomer is there under the physiological conditions, because the stereo center is alpha to the carbonyl group. You can see here that this stereo center which is present to alpha position to a carbonyl group, jahan carbonyl group, where the carbonyl group is present, just on the alpha position that stereo center is present. So whenever we are using the pure form, which is the R form, again it is reacting with the, or again it is forming the S form also by these type of physiological conditions. So only according to configuration we can see that properties are changed and how they can describe. And these are some of the examples you can see about the optical isomers which may differ in the physiological activity. Here we have taken first example, which is a benzomorphia. Here this is a minus benzomorphia, it's a plus benzomorphia. Minus benzomorphia, it seizes the pen, it's unhabituational and it's a faintly pen erasing. Here in the next example, minus benzopyrroldiol, this shows the strong carcinogenicity, and the same time plus benzopyrroldiol, it shows no carcinogenicity. And L-asparagine, it's a bitter, which we have already seen in last slide, and D-asparagine, which is a sweet in taste. Here this is one of the form of diltiazem, that is a SS form, which is effective in relieving the myocardial infarction. So these are some of the optical isomers which vises or which have the difference or differ in the physiological activity. So in this part of stereochemistry we have seen about the constitutional isomers as well as stereoisomers. In that stereoisomers we have seen the two parts of that, enantiomers and distereomers. After that we have seen about the specific rotation, what is the plane polarized light, and in specific rotation how we can calculate and we can describe about the racemic mixture, and that racemic mixture value, and by the specific rotation, and specific rotation of that racemic mixture value was 0. After that we have seen some of the examples which are related to optical isomers and how these optical isomers can differ in the physiological activity, and simultaneously Fischer projection of the 2-butanol example, in which type of a rotation is a allowed process and which is not allowed. And when we are saying about the priority, how we have to describe about the priority, then we already said, then if the fourth priority group is present on the horizontal line, at that time the reverse type of a configuration we have to describe and determine. So in this way, these are some part of the stereochemistry I presented here. Thank you so much.